Hello, it's Miss Owen here on behalf of Miss Emblem. I'm going to help you fill in your foldable from today. Alright, so in example 1 it says in 1990 approximately 29,816,591 people lived in California. The population has grown by approximately 1.28% per year since then. Estimate the population in 2007. So what I like to do is I like to kind of label my variables first so I can figure out what we are looking for. We do not know our ending amount. That's what they want us to estimate. Our principal, or our starting amount, is the 29 million odd people. Now my rate is the 1.28%. I'm going to go ahead and change that into my decimal. And N is the number of compoundings per year. If they don't mention anything, that N is just 1. And the T is times. Well, we're looking for 2007, and when we started it was 1990, so that gives me 17. And now I can plug it into my formula. A equals the 29 million times 1 plus my rate, which was 0.0128 over 1 times 1, or to the 1 times 17. Now you'll notice that when the n is equal to 1, you can almost ignore the n terms, but for your purposes today, I'm going to go ahead and leave it in there just to help you. Now when you type it on the calculator, they give you a E, and just as a reminder, that when you get an E to the 7, that scientific notation means I need to move it over 7 places. 1, 2, 3, 4, 5, 6, 7. So I need to add 2 zeros. So really my approximate solution is the 13,600 people. As a general rule, it helps if you remember to add your units so that you know what you're talking about. Alright, let's look at example number 2. Alright, so this is our decay formula, and notice that all that changed was it went from a plus sign to a minus sign. So I'm just going to read through it. You buy a new car for $22,500. The car depreciates in value 25% each year. Find the value of the car at the end of each of the following years. So what's happening is they want us to change our the number of years, our T value. So our T in this one would be 1, our T in this one is 3, and our T in this one is 5. And so then the rest stays the same. So our principal amount, we're still looking for the A. Our principal amount is the 22,500. The rate is the 25%, which is equal to 0.25, and our N is going to be 1 again. So on this one, we have A is equal to the 22,500 times 1 minus the 0.25 divided by 1, which what you notice is 0.25 divided by 1 is still 0.25, and then 1 minus 0.25 is 0.75, so this is going to be the decay. That's how the decay comes in. And then we have 1 times 1, which is essentially just 1, and we get our answer, and when we type it in on the calculator, is 16,875. Now you'll notice that the car dropped almost $6,000 in value. So let's look at the next one and see what happens over the course of another 2 years, how much the car drops in value. So now all we're doing is we're changing the T. The N is staying the same, it's still staying 1, and then we just have 1 times 3 here, gives me 9,492.19. So it dropped another, so in 2 years, so the first year it dropped almost 6,000. The next 2 years it drops closer to 7,000. which you're seeing now that that's over 2 years, so it's declining less. So let's see if we add another 3 years into or another 2 years into the equation. We're going to just change our exponent. So 1 minus 0.25 over 1 times to the 1 times 5. And that gives us 5,339.36. And remember, these are all talking about money because we want to find the value of the car, which is how much it's worth, or the value. So this dropped to almost 4,000, so it's not losing as much because it's decay. It's going to approach an asymptote where it gets closer and closer to a certain number. Alright, let's look at example number 3. It says, this is compounding interest or growth, and so now this is where the N comes in. We're talking about compounding. So you deposit $5,000 in an account that earns 3% annual interest. Find the balance after 10 years if the interest is compounded with the given frequency. So everything is staying the same. We're still trying to find our A. Our principal is $5,000. Our rate is 3% or 0.03, and then our N is changing each time, and then our T is after 10 years, so our T is going to stay the same at 10 this time. So we're going to go in this one, our N is annually, so that means 1. Monthly means that it happens 12 times per year. Quarterly means we're talking about 4 times per year. Weekly means 52 times per year. Daily means 365 times per year approximately. We're going to ignore the leap years here. And then continuously, we are going to use this equation for our continuous one. So these go together, and I don't even need to write my N because my N uses E, which is known as Euler's number. And now I get to plug in. Alright? So I have A is equal to my 5,000 times 1 plus my 0.03 over 1 times 1 to the 1 times 10. And that gives me, remember this is all money, so we're looking at $6,719.58. And we're going to do the same thing for all of these. This is going to be the 5,000 times 1 plus 0.03, and now we're going to divide it by 12 because this is where my N comes in, and I have this to 12 times 10, and that gives me $6,746.77. Now you'll notice that the more often it's compounded, the more we're going to get. So this went from monthly and from annually to monthly, and now we're going back down to quarterly. So this isn't happening as often, so I'm going to assume that I'm going to get a number somewhere in between these two. So I have A equals 5,000 times 1 plus 0.03 over 4 to the 4 times 10, and this gives me 6,741.74, which, just like we thought, it was $5 less. Alright, now we're looking at the weekly. We get the 5,000 times 1 plus 0.03 over 52 to the 52 times 10. And we're going to think that it's going to be more than the monthly, and we are correct, but just by a little bit. It's just a few dollars more, about $2, a little less than 2. Alright, now daily, let's think it's probably going to go up a little bit more again. 5,000 times 1 plus 3% divided by the 365 times being compounded to the 365 times 10, and we get 6,749.21. Alright, the last one, this is where we're going to have to use the continuous function. So we have A, and my P stays the same. My P is still 5,000. My principal amount didn't change. Now, how I'm doing this is I'm going to use E, which is Euler's number, which means it's compounded continuously. So moment by moment it's being compounded, and we have it to the R, which was our 0.03, our rate, times T, the number of years, which was 10, and now we have 6,749 and 29 cents, which, if you'll notice, is just a little tiny bit more. Alright, last little page, we're going to put it all together. This is kind of a front page if you fold it and cut it like you were supposed to. A is going to be equal on this one to the P times 1 plus R over N to the NT. A equals P times 1, and just like I said before, all it changed was from a plus to a minus. And now we have A equals P times E to the RT. And there we have it. These are our three, and give me a moment while I rotate the picture for you, that way I'm not writing sideways. Alright, I'm back. Alright, it says ecologists have determined that a national forest can sustain a maximum population of blank deer. Now I'm going to look over here, and it looks like my asymptote is approaching 900, and if I look down here at my K value, it is 900, so it's approaching a maximum population of 900 deer. When the forest is first designated as a wildlife preserve in 1985, that would be at time 0, there are how many deer? Well, you can look on there, it's a little over 200, and if I plug in 0 to my formula, I'm going to see that I'm going to get approximately 214 deer. Now, if you guesstimate and say like 210, I bet Miss Emblem would be fine with that. Now, using this model, there will be approximately how many deer in 1988? Well, that's another 3 years, so I'm just going to look on here at 3, and it looks like it's about here, around 750, and if I plug in 3 into my formula here, I see that it's 752. Now here's the key question from this example. It says, why is the growth of the deer population approaching a horizontal asymptote? So it's a limited growth or a reflected decay, which we know about decay problems is they approach the asymptote. Alright, and so because it is a reflected decay, it is growing. The numbers are growing, but my rate that they're growing at is getting smaller and smaller, so they're not growing as fast. It's approaching that asymptote, and so we know that it is getting closer and closer to the asymptote, and so that's where the reflected decay comes in, that even though it's growing slower and slower, so the rate or the change is decaying. And I will write that in, and then you can fill it in just a second. Alright. So, there you have my little explanation written out. You can use your own words, but just realize that when you see that this is decay here, and then we have our A value as a negative value, so our absolute value of B is less than 1, which means that the value is in between 0 and 1. This 0.6 is a decimal or a fraction, and we have our A value is negative. You're going to see it looking like an upside down or a reflected decay graph. Alright, so you can pause this and fill in the rest of it, or I will also be posting the PDF for you. Hopefully you find this helpful. Have a wonderful day.